Okay, so this is our first lab, yeah, and what we're going to do with this lab is we'll figure out how the mole concept work. Okay, we'll try to understand in much more detail about mole concept. Okay, give me 1 second. Okay, so the first thing we do is open up this lab. This is called balancing equation. Yeah, you probably can see it on the top right here. It's called balancing equations lab. Yeah, and so the first thing we do on the top is click make ammonia. Okay, so click ammonia here, then at the bottom click balancing scales right here. Yeah, so you get these two different scales on here. Okay, now what we do is this is the reactant box, this is a product box. Yeah, and balancing scales is going to give you reactants on the left, reactants on the right, reactants on the left and reactants on the right, so on and so forth. Okay, so the first thing we do is set the coefficients of each of these to 1. So we make nitrogen 1, hydrogen 1 and ammonia 1. Okay, the number of different atoms on the left and the right are shown at the bottom on the balance scales. Okay, it should be obvious from the balance scales at the bottom that these coefficients do not balance the equation. Correct, so there are 2 nitrogen on the left and there is 1 nitrogen on the right. Okay, there are 2 hydrogens on the left, whereas on the right there are 3 hydrogens. Obviously the reaction itself, which is this reaction, is unbalanced. Yeah, so we need to balance this equation. To increase the number of nitrogen on the right, we basically increase this coefficient to 2. Okay, so now we have 2 nitrogens on the right, 2 nitrogens on the left, so the scale here is balanced. Okay, but look what happened with the hydrogen got even more unbalanced. Yeah, so we need to adjust the hydrogen. Okay, so obviously there are too few hydrogens on the on the left hand side, so we need to increase the coefficient of hydrogen to. So can you tell me how many hydrogens we're going to need on this side? What should be the coefficient? Okay, let's see if you're saying 2 hydrogens. Let's see if that helps. 2 hydrogens and the scale is still unbalanced. Okay, so we need 1 more hydrogen. Obviously there are 6 hydrogens on the right hand side, we only have 4 hydrogens on the left hand side, so we need 6 hydrogens. We increase that to 1 and then get a smiley face now. Okay, so now the reaction is unbalanced. The reaction is balanced. 2 nitrogen on the left, 2 nitrogen on the right. Yeah, 6 hydrogens on the left, 6 hydrogens on the right. Okay, so what are the implications of balancing equations? Clearly the number of atoms of nitrogen and hydrogen from the left and right must remain same. Correct, there are equal number of hydrogen atoms and equal number of nitrogen atoms on left and right. Correct, we can see that balancing on the scale, 2 here, 2 here, 6 here, 6 here. Yes, you have to type your answer, Sahil. Okay, as I said, I cannot switch right now, but you have to type your answer. Okay, you are asking what is the difference between the lowercase 2 and 1 in front. Is that correct? Okay. Now this actually is a molecule, and in this molecule there are 2 nitrogen atoms involved. Okay. Similarly, you have this is a molecule, one molecule, yeah, and in this one molecule you have 2 hydrogen atoms involved. The number in front indicates how many number of those molecules you have. Okay, similarly, this is NH3 is a molecule. You can see the structure right here. Yeah, you have NH3 is a structure, and in the number in front is how many number of ammonia molecules you have. Is that clear? Okay, so basically we understood that the number of atoms on the left are equal to number of atoms on the right. Yeah. So what we can infer is that the atoms are the smallest part of the chemical reaction. Correct? You cannot break the atom into half. Yeah, you cannot say half a nitrogen or half a hydrogen, because that kind of species does not exist. Yeah, atoms are the whole number. Now in this case, as I said, nitrogen molecule is made up of 2 atoms. Yeah, so that's atom is the unit of this chemical reaction. Okay, the mass is conserved from the left to right, and as you can see, basically you add nitrogens and hydrogen, you get the total mass on the left hand side. So you have 2 nitrogen atoms, 6 hydrogen atoms on the left. Yeah, similarly you have 6 hydrogen on the right and 2 nitrogen atoms on the right. Yeah, so since the number of atoms are conserved, the mass is also conserved. Okay, is that understood now? Okay, let's move on to second lab. Okay, this is our second lab, and this is again a lab called reactant, products and leftover. Okay, it's right on the top here. Okay, now in the instruction it says switch the tab to real reaction. So we switch, so there are different tabs here. Yeah, you can play around basically, but for now we're gonna switch it to real reactions. Okay, then we switch this to make ammonia. Okay, again you can always play around, you work with water, methane, whatever, but for now we're going to work with ammonia, because in the earlier lab we worked with ammonia, correct? So we'll work with ammonia again. Okay, so now let's set up the equation we just did with setting the coefficients on the left hand side with 1 nitrogen, yeah, and 3 hydrogens. So we do 3 hydrogens, yeah, and these are the coefficients that we had. Basically we in the previous reaction we exactly had the same thing, correct? 1 nitrogen molecule, 3 hydrogen molecule gives you 2 ammonia molecule. Okay, so we set up this similar reaction now. Okay, or actually same reaction. Okay, now we see that there are 2 molecules of ammonia are formed. Yeah, let's now choose 2 molecules of nitrogen and 6 molecules of hydrogen. So we increase the number of molecules here from 1 to 2 for nitrogen, and then hydrogen we make 6. So we are basically doubling the number of molecules on the left. What happens to the number of molecules on the right? They also double. Okay, so now you have 4 molecules of ammonia. Okay, so what we have done is basically we have multiplied this entire equation by 2, correct? So now we have 2 nitrogen, 6 hydrogen and 4 ammonia molecule. Okay, you can similarly get 3 ammonia molecule and increase this to 9. Okay, so now you have 9 hydrogen molecules on the left, so you get obviously 6 ammonia molecule. You can see right here, yeah, 6 ammonia molecule. So now you have multiplied this number by 3. Okay, so every time you do that, you get subsequent number of product on the right hand side, correct? Now can we multiply it by 12? This entire reaction we multiply it by 12, right? We can also multiply it by 12. 12 is a dozen, so you can say we can multiply this entire number or this entire reaction by a dozen. Yeah, so you have 1 dozen of nitrogen, okay, you will have 3 dozen of hydrogen, that will give you 2 dozen of ammonia molecule. Is that correct? Yeah. Can we also say that we can multiply this equation by mole? So you'll get 1 mole of ammonia reacts with 3 moles of hydrogen to give you 2 moles of, sorry, I think I said ammonia here, it's actually nitrogen. Yeah, so 1 mole of nitrogen reacts with 3 moles of hydrogen, gives you 2 moles of ammonia. Is that correct? But what is a mole? Mole is a number, right? Just the way dozen was. Dozen meant 12. So the mole is also a number. 1 mole is basically 6.022 into 10 to the power 23. Yeah. So that many number of molecules of nitrogen. So 6 into 10 to the power 23 molecules of nitrogen reacts with 3 times 6 into 10 to the power 23 number of hydrogen molecules, gives you 2 times 6 into 10 to the power 23 number of ammonia molecules. Yeah, 1 mole is that number, and so basically that's what it signifies. Correct? We are just multiplying with a different number. Yeah. So basically you can multiply this number, this equation by any number. Yeah, but for as you know, in reactions there are many molecules. Yeah, millions and billions and zillions of molecules in any reaction. Even a small quantity contains very large quantity of molecule, very large number of molecules. Yeah, we saw that in the last class. So it makes sense to express these quantities in moles. Okay, so that's basically is the crux of it. So you can say, instead of saying 1 nitrogen molecule, you can also multiply it by a number of moles, and you say 1 mole of nitrogen and 3 moles of hydrogen gives you 2 moles of ammonia. Okay, so mole is nothing but a number. It's a very large number nonetheless. It's a very, you can't even imagine. Yeah, billion is what, 12 zeros, and 10 to the power 23 is much more than that actually. Yeah, go ahead, Sahil, you can always type your question. Yes, 6.023 into 10 to the power 23 atoms. That is correct. That is 1 mole. Okay. All right. So basically now this is, we're done with the lab. Yeah. Basically now what we'll do is basically look at what else we can do. You can obviously play with different water or methane or whatever, balance the equations. You can also play with sandwiches here. If you, let's say you want to make a sandwich. Yeah, this is the example that was from the notes. You want to make cheese sandwich. Okay, and the concept is very similar to that of mole. Basically, let's say you want to define the sandwich first. Okay, for a sandwich you need 2 breads and one cheese, and maybe you want to make a meat sandwich, for example. Okay, so 2 breads, 1 salami, I guess, and 1 cheese. That gives you 1 sandwich. Okay, so you need bread, cheese and meat in that ratio, 2:1:1, to make 1 sandwich. Obviously, if you have, let's say, 4 bread, okay, so let's make 4 bread, and you have only 1 meat, okay, and maybe 2 cheese, still you can only make 1 sandwich, right? Because the other things are going to be left over. Okay, same thing with chemical reactions. Yeah, you will have leftover if. So here, what is the limiting factor? Meat is the limiting factor. If you have more meat, obviously you can make more sandwiches. So let's say you have 1 more meat, now you can make 2 sandwiches and nothing is left over. Correct? Same thing with chemical reaction. If you have, doesn't matter how many hydrogens you have, let's say you set nitrogen to 2, yeah, now you can make molecules which is going to be equivalent to the number of nitrogen molecules. Doesn't matter how many hydrogen molecules you have, yeah, so you'll have leftover hydrogen molecule, because there is no way you can use these hydrogens to make ammonia. Okay, so this is leftover. The limiting reagent for this reaction is then the nitrogen. Okay, because that is what doing the limiting the formation of ammonia. Okay, similarly you can switch if you have a lot of nitrogen but very few hydrogen. Obviously now in this case nitrogens are going to be left over, hydrogens are going to be consumed, so the limiting reagent in this reaction is the hydrogen. Okay, doesn't matter, remember. So now look at this reaction. Yeah, you have 8 nitrogen and 9 hydrogens. Okay, and so if you just look at the number, you would think that nitrogen should be the limiting reagent, but it is not. The limiting reagent is did I make something wrong here? Yeah, so yeah, limiting reagent is still nitrogen, correct, even though it is in small number. No, sorry, yeah, the limiting reagent is hydrogen, even though it is larger. Okay, even though it is larger. Sahil, you have to make the molecules are whole number, you cannot split, correct? So there are only possible ways of combining these, so for each molecule, so here you have, for each molecule, to make 1 molecule of ammonia, or to make 2 molecules of ammonia, you need 3 hydrogen molecules and 1 nitrogen molecules. Yeah, so this is the reaction. If you have more nitrogen, doesn't matter, because you don't have any more hydrogen here. Yes, the hydrogen is the limiting reagent. What I want you to notice is that here the hydrogen is more than the number of hydrogen molecule is more than the number of nitrogen molecule, but still hydrogen is limiting reagent because it is being consumed. For each nitrogen atom you need 3 hydrogen atoms. Okay, so obviously you have to look at the mole ratio, not the actual number. Yeah, you have to look at the mole ratio. Here the mole ratio is 1:3 for each ammonia molecule. Okay, is that clear? It's kind of like making the sandwich, right? I mean, if you have doesn't matter how many breads you have, okay, doesn't matter how much cheese you have, you can only make sandwiches because that's what you have defined. Yeah, you have defined this is the reaction. Okay, and so you have only 2 slices of meat, so you can only make 2 sandwiches. Everything else is going to be left over, and this happens in your refrigerator every day, right? If you're sometimes you run out of bread, even though you have meat or you have whatever, salad, whatever, but you don't have bread, you cannot make sandwich, because then in that case bread would be the limiting reagent. Sometimes you want to make bread butter jelly or bread and jam, butter and jam sandwich, correct? You have butter, you don't have jam, you have bread, you cannot make a sandwich because you don't have butter, sorry, you don't have jam. Okay, so jam is the limiting reagent in that case. Okay, defined, that's what it is. Anything that is less in quantity, okay, anything that would limit a reaction, and or limiting reagent is always going to get consumed, all of it. Okay, that's limiting reagent. So nothing of, you can see that there is the meat is not left over, it is gotten consumed. Okay, and that's limiting reagent. Yeah, Aldrin, can you hear me? I haven't gotten a response from you.